Hello and welcome to the first episode of our series on trigonometry. Now in this video today I'm not really going to do any calculations, but I am going to attempt to explain to you what trigonometry is all about so that you can have the background info. Obviously you would be able to do the calculations without knowing or watching this video, but the groundwork is going to make it a lot easier to understand when moving forward. So I would suggest looking at this video and just finding out. So the thing trigonometry is all about, obviously if you don't know this yet, it's all about triangles, people usually say, but it's not really about triangles. It's more about angles. And the reason I say that is when we draw a normal triangle like this, let's say a 90-degree angle, then let's say we have a 30-degree angle. It's all good and well to work in this let's say on this triangle, but sometimes we want to find out when the angle is 0. And if the angle is 0, there's no triangle. Or if the angle is 90, if this angle goes up to something like 90, then suddenly we don't have a triangle anymore, and people are like, oh, but it's a bit confusing. So it's more about the angle itself than the actual triangle. So let's get started. I'm sure by now you know what the Cartesian plane is, and if I showed you something like this, you know what this is. So basically we have the normal number line that you're used to, which is the x-axis, and this is the horizontal plane, and we have a y-axis which just tells us how far we go up or down. So x would be horizontal and y would be vertical. Now if I drew a line, which I did here, and this line represented something that moved maybe from here to there. Let's say it's a ball. I threw a ball from here and it's there. You would agree that I can, let's say I can break this down in two parts. There's a certain distance the ball moved on the x-plane, and there's a certain distance it moved on the y-plane or the y-axis. So in this case, if I start from 0, 0, which is the origin, and I wanted to tell you how far I ran, obviously you should have some, let's say, knowledge of gradients. So you know the gradient would be the change in y over the change in x, or some people talk about rise over run, where rise would be up and down, and run would be forward and backward. And in this case, rise would be any movement in the y-axis, whether it's up or down, and run would be anything in the x-axis, whether forward or negative, forward or backwards. Okay, so let's say I have a line here, and this has a certain angle. I don't know what this angle is. Let's make it a theta. Okay, so theta is just a variable we use, just like you got used to using x, y, z, a, b, and c. Now we have a new variable that we kind of talk about when we speak about angles, and it's just a Greek letter. So it's nothing special. It's not like a constant where it has a set number like pi. Pi has a function, like pi has a number that's the same and it's repetitive, etc. But pi is always the same, whereas theta is not going to be. It's just a variable. Okay. So let's say I'm throwing a ball at a certain angle from this point to that point. Let's say this is point A and this is point B. I'll just make a B here and then make an A here for the start. I can say that this ball traveled a certain distance forward, and I can figure out how far forward it traveled by looking at this, like going down to the x-axis all the way down, and that means I have to obviously I have to go straight down, so that would be a 90-degree angle. So if I wanted to find out how much I ran, then it would be this distance, and then how much I rose, it would be the distance from here to there. Okay, so what does this have anything to do with trigonometry? Now, trigonometry is the study of this angle, and what we're going to see is there's always a relationship between these angles. So let's just put this guy over there, and let's just draw one here to also show. Okay, so it's actually more about going from there to there and what this angle is. But we're going to see there's a certain relationship between this side and this side and this side, etc. Now, before we start, we just have to kind of always name our triangle. So this triangle's name is Bob. No, I'm just kidding. We have to name the sides of the triangle. You can call him Bob, but we have special names for triangle sides. So you know, in a right angle triangle by now, this side is going to be the longest side. So you work with Pythagoras, so you know this side squared is the same as this side squared plus that side squared. But we have special names. So the longest side in a right angle triangle is called the hypotenuse, hypotenuse angle. Hypotenuse side. So that's the longest side. If I use this as my reference angle, you would see that if I increase the size of this angle, then this side would get longer. Pretty simple. If this angle gets bigger, this side gets longer. And if this angle gets smaller, this side gets smaller. Pretty basic. So this angle has a direct influence on the length of this side. And this is the opposite side. So this one looks over there, and this is the opposite side. And then the one touching the actual angle that we're talking about or using as our reference angle, that would be called the adjacent side. So I actually am more interested in the let's say the movement from A to B at that angle, but to break it up for myself, I need to draw, like I did here, kind of a line down. So that's where the triangles come from. They break the triangle or the distance I'm traveling from one place to another down in two parts. The x-axis part or the horizontal part and the vertical part or the y-axis part. Okay, so if you look on your calculator, you see there's these weird things. You might have not noticed them. Well, you would have noticed them and you might have asked someone like what they are, and people say, oh, it's trigonometry, but it says sin, cos, and tan. So that's what we're going to talk about. Today we're going to more focus on sin. The other videos we're going to focus on cos and tan, just what they mean and why they're there. Okay, so I'm just going to take this away. So when I say sin will also always give me an idea of vertical movement. So if I look at my little Cartesian plane here, sin would always give me an idea how far up I moved. Now what does that mean? So the sine of an angle, that's kind of how we write it. We usually use sine and then we make this little angle. If we knew it was 30 degrees, I might go sine of 30 degrees and that would have a number attached to it. But let's just start with unknown value. The sine of this, this unknown angle would be kind of the relationship between the opposite side and the hypotenuse side. So as a ratio or as a fraction, would say it's the opposite over the hypotenuse. Now don't worry about remembering this. There's a cool way that we'll show you later on how you can remember this. It's called SOHCAHTOA, and you'll be like, what is that? I'll show you later. But for now, I just want you to know that if I'm thinking about the sine of an angle, it has something to do with this movement or the displacement from, in the vertical and the y-axis. Now I have a little triangle here that I printed. So let's see what I mean by it. Okay, what is going on here? So in this case, I have a triangle with there's a 90-degree angle. Both these are right triangles or right-angled triangles. Now in this case, I have a very small angle. And if I look at the length of this opposite side, and what I did is I actually copied this length and I just put it on this one. So if you look at this, you can see that the opposite side covers only a very small side of the whole hypotenuse side. So sure, just notice that. We'll look at the details now. When the angle is bigger, then I see, wow, the opposite side, if I put the opposite side on the hypotenuse side, it covers a lot more. So when I think about the sine will always give me an idea of how much vertically I'm going. So if there was someone playing basketball, and there's a hoop, and here's a ball, and he's trying to throw the ball in there. The sine value for this, something, if I drew a little triangle here, the sine value here would be bigger. Now don't worry about what the number is or anything. I just want you to realize that there is a sine. I'm going to put it in the calculator now, and then you can see there's a value attached to a certain angle. But if I'm close and there's a lot of vertical movement, or the rise, in this case the rise, is a lot more in comparison to maybe the run, I will have if I'm working out the sine of this angle, I'd get a higher number. Okay, just notice that. If I was standing like right over here and I had to throw the ball there, this sine would be a lower value. So this small angle would be lower. So let's just use the calculator and use two extreme examples to show you. So in this case, I'll start with these two. Or maybe no. Let me start really extreme. Let's go really extreme. So if I were to make this angle smaller and smaller and smaller and smaller, eventually you'd see that let's say this is a really small angle. This is 1 degree. You can see that this side is kind of, eventually, if I make this angle 0 degrees, this line will actually just fit on that line, and this whole opposite side, it's getting smaller, it would disappear. So it would look like this. If I drew an angle, a 0 degree angle, it looks like this. And if I looked at this function or this equation and I said the sine, this angle is 0 degrees. So I say it's 0 degrees is opposite. Now, do I have opposite side? No, it kind of disappeared. Check. I had the big angle and I had a long opposite side. Then it became smaller. The angle was smaller, and then suddenly the opposite side got all smaller and smaller and smaller, and eventually it's gone. So there is an opposite side there, but it's actually 0. So the opposite length would be 0. And it wouldn't matter what the hypotenuse was, if it can be 10. So let's make it 10. Anything, if I say 0 over 10, that would be 0. So we'll see that the sine of 0 is actually 0. Now check, let's see if I'm not lying to you. If I push sine 0, it just stays 0. Now what would happen if I actually made this angle, I took it all the way to 90 degrees. So if it moved higher, the opposite side would increase, all the way till the opposite side actually fit onto the hypotenuse side. So what would that look like? It'll just be a line like this, because I moved 90 degrees in that direction. And if I had to do the sine of 90 degrees, then suddenly the sine value would, well, it's the hypotenuse over the opposite over the hypotenuse. The opposite line is actually lying on top of the hypotenuse line. They're both the same. So if the hypotenuse was 10, the opposite was, let's say the hypotenuse was 10, the opposite side would be 10 as well now. So we'd have a fraction where the top number is the same as the bottom number, because both lines are the same length. So then the sine of 90 degrees would then be, what's 10 over 10? It's 1. Okay, x over x, 10 over 10, 5 over 5. So let's just check I'm not lying to you. If I look at sine, and I type the sine of 90 degrees equals 1. Okay, so in trigonometry, it's gonna, when we work out the sine of a certain angle, it's kind of telling me the portion of this side if I'm putting it on that side. So I'm just using my initial graph here. It will tell me, obviously I moved from A to B. So the sine of this angle will tell me how much of this actually covers that. Now there's one special angle, which is the 30-degree angle, and we see something really special happen there. So this is my normal angle, so let's say I moved from here to there. If I were to take the sine of 30 degrees, just take this away. If I took the sine of 30 degrees, sine of 30 degrees, something really interesting happens. This length fits on this side exactly twice. Again, it's not something that you should know now, but it's something that you will definitely have to know later. At AS level, you should definitely know that. But for IGs, I think you should be aware of it. You always have your calculator with you, so you should be able to actually just work it out. But let's see, what do we expect the sine value to be? Again, this is not necessarily something, we're not doing calculations today. In this video, if the only thing you take away from this video is that you understand when we're working about sine, then we're working up and down. We're trying to figure out like vertical displacement. That's a good takeaway. So let's just go dive a little bit deeper, and let's say, what do we expect? If I were to actually measure this triangle, this is a 30-degree angle. If I measured that, let's say I measured that and it was 10 centimeters. The opposite side was 10. We know that the sine of an angle is the opposite over the hypotenuse, and in this case we know this is our reference angle, so this is the opposite side. So let's say I measured this as 10, and this would be my hypotenuse. It would be really interesting because I can measure this would be 10, and that would be 10, and that would be 10. So I kind of made it different colors, so you can just see they're the same length. So we would have a 20. It doesn't matter what if this was 4, this would be 8. If this was 10, it's 20. If this is 100, that would be 200. But at 30 degrees, we just always see this constant number. So what do you expect? What is 10 divided by 20? Probably a half, right? So 0.5. So let's just check if I'm not lying to you. So sine of 30 is 0.5. So it means that any time, it doesn't matter how, if I had an angle that's 30 degrees, it doesn't matter how long this line is. It can be short, or it can be, okay, let's just take this off, or it can be very, very long. If I were to measure this distance, it would always fit in this distance 2 times. Or if I measured this distance, it would measure in this one 2 times. So the 30-degree angle is very special. It's just nice to use it as an example to show that, you know, what's happening here. There's like ratios in between. But let's quickly test our knowledge. Let's see if we kind of understand. So if you understand what I'm going to do now, I feel this is good enough for you to just be like, yeah, I got this. Okay. Gonna draw two triangles. So let's say we have a triangle like this. And it doesn't matter what the angle is. And then I'm gonna draw a triangle like this. And this is a different angle. I made both theta now, but they have different angles. You can see this is a small angle, this is a large angle. And let's say I just make up some sine values. Let's say the sine, I'm gonna make up 2 values, and then you have to kind of guess which one fits which one. So let's say this is 0.8 and this is 0.2. These are just made up numbers. Which triangle would have the bigger sine value? Would the triangle with the smaller angle have a bigger sine value, or would it have a smaller sine value? So what does sine tell us? Sine tells us a lot about how much I'm moving vertically. So if I'm moving a lot vertically, then my sine value would be bigger. We saw that the sine of 90 is 1. And if I have a smaller angle, then the sine value became smaller. And if I had a 0-degree angle, then the sine would actually be 0. So sine is very intuitive. Bigger angles, bigger sine values, smaller angles, smaller sine values. So you should now know, if we had to write down which triangle goes with what, this triangle has a smaller angle than this one, so I would assume the sine value would be smaller. Again, you don't have to know the sine values. You just have to know that small angle with sine, small angle, well, small sine value. And then this is obviously the bigger sine, or the bigger angle, and then the sine angle would be bigger. So these two would go together and those two go together. So let's just do a couple of tests. I said the sine value of a smaller angle. So let's say the sine value of 10. If I write that, that's like 0.17. Okay, so this was the sine of 10. So it means any time that I have an angle that's 10 degrees, the sine value would be 0.17. What that basically means is if I put this on there, it would cover, like, I don't want to use the word percentage, but it would cover 17% of that line. Then if I had a bigger number, let's say the sine of 80, that's a bigger number. So the sine of 80 is 0.98. Okay, obviously it's a very longer number, but can you see that there's a correlation between this angle and this number, and this angle and this number? Now, for what we're going to do, we're basically initially just going to work in, firstly, we're just going to work in this first quadrant, right? And the angles in this quadrant is everything from 0 to 90. So when we look at this quadrant, the sine values would go from 0 to 1. That's kind of the range. We would never have a sine value greater than 1. We can have one, like in the next videos, you'll see that sine values range from -1 to 1. That's kind of the range. So we can never put in the sine of an angle and get 2. And let's just think about why that is. Again, this is just a lot of extra information, but let's just think about it. Why would I never have a sine value greater than 1? Because sine is how much of this line fits on this line. And this is always the longest line. I could never draw a triangle where this line is longer than that line. I mean, how will that even look like? I mean, it doesn't work, because as soon as I do that, then this becomes the hypotenuse, right? The longest one by definition, and the one across the 90-degree angle, is the hypotenuse side. So I could never have a fraction, let's say, I could never have the sine of an angle with my opposite side being larger than the hypotenuse side, because it can only be as big. And then if the angle gets smaller, then this side just gets smaller, but this stays constant. So that's the reason sine values would always go, well, I told you in the first quadrant, for anything between 0 and 90 degrees, we would have it that the sine value would either be 0 at 0 degrees or 1 at 90 degrees. So it always varies in there. Yeah, so I think that's it. Like I said before, sorry for repeating this again. You should just have an idea that sine gives you an idea of vertical displacement.